This is about apportionment, which basically means how to distribute a certain number of resources to a certain number of recipients. Because this entire section is on voting and apportionment, we will come up with Parliament, that is the House of Representatives, at some point. And again, mostly I will focus actually on that, but there's a little bit of an introduction here. We also will come across standard divisors and standard quoters. They just help us to compute the apportionment. So here, that looks like a nice example here with the cake. You have a cake and you cut it into 12 pieces. That's relatively easy to do. It turns out there's only 11 people at the party. So how do you do that? Well, you do it with the 12 piece. Well, you give it to one person, so that person gets 2, or maybe you cut it into 11 small pieces, or you cut the cake in the first place into just 11 pieces. So a little bit harder to do, by the way. But in any case, you come up with a fine solution. So that's another way of apportioning, well, resource to a certain number of recipients. And I'm going to go through here, and yes, there are more examples here, and I think I want to go actually, it's coming up here. There we go. And there it is indeed, the House of Representatives. So as it says here, there are 2 houses on Congress in the United States. The Senate is really easy. Every state gets 2 senators. There are 50 senators, hence the Senate has 100 members. House of Representatives is somewhat harder to do since, as it says here, the Apportionment Act of 1911 and then the Reapportionment Act of 1929, the House of Representatives has exactly 435 members. There are 2 exceptions when Hawaii and Alaska joined in 1959 and 1961. They were actually 437, but these are really 2 small exceptions that I will ignore. In any case, this kind of says, hey, here's an introduction on what should happen. You ought to apportion these 435 seats across 50 states, and you have to do it as fairly as possible. So that's the problem here. And then there's one more problem, which is, of course, you cannot give away a fractional seat. You cannot cut a person into half. All right, so let's get on here a little bit. I'm scrolling through here. I've written down whichever page I want to look at in our textbook. Yep, there we go. So here we go. Again, apportionment problem becomes more complicated and interesting when the resource is an integer number, such as 34 laptops across a certain number of classrooms in a school, or 435 representatives in the House of Representatives, and thus allowing fractional parts is impossible. You cannot cut a laptop into 2 pieces. So going through here, they actually do the laptop problem. I believe it's on the other page here. Yeah, there it is. They do it actually here, and to run through this one here, 34 laptops apparently due to a grant, and they tried to distribute it across 6 rooms. Well, 34 cannot be divided by 6. It also doesn't help that the room capacity is different. So what they do is they use this standard quota here, which they divide by the standard divisor. That's a 4.88 here, and they come up with these numbers, and then you have to round them. Well, if you use the traditional rounding, which is 0.5, you round up, 0.49, you round down, you come up with these numbers here, and when you add them, 35, it's oops, 1 too many. We don't have 35, we only have 34. So one of these here ought to be rounded down, and we can already see that the first 2 here, this solution here is actually relatively simple. These 2 here, they already rounded down to 6 and 5. It's the other 4 that have been rounded up. We can see that the closest one to 0.5 is the last one here in the classroom of only 27 people. So unfortunately, that's the one that we have to decrease by 1. So technically what we need to do is take 1 off from this one. So minus 1. As I said, sometimes these problems are not as easy as this one. All right, again, scroll down to the next page that I want. It's quite a bit down. Let's see. Getting there, I think. There we go. All right, so here they actually go through these different apportionment methods that have been used for elections and then for the apportionments of certain houses. And the ones that you come across here are named after these famous people. Hamilton, Jefferson, Adams, and Webster all served their country, two of them as presidents. And it turns out actually that there's a total of 5 methods that have been used for the House of Representatives since 1790. The 4 that are listed here, and the one missing here, Huntington Hill. Well, that's the one that I actually want to talk about. That's the one that has been used since 1941. For some reason, it's actually not in our textbook, and it's actually, I believe, not that hard to do. So what they do instead is here in this math book, and other math books too that talk about apportionment, they use all kinds of other examples, such as the country of Imaginaria, or they use Hawaiian school districts. All good, but hey, what about something here? Instead of Imaginaria, give us the actual House of Representatives. As I said, I'm going to do that. And talking about Honolulu and Hawaii, that's not so far-fetched. All right, let's go on here. Which one I want? I think the next page is coming up here. There we go. Fairness and apportion methods. I like this kind of chart here. It shows us the 435 seats in the House of Representatives, and it's color-coded by each state, and they didn't list for which house this is. Is it the 85th house? Is the 110th house? Whatever. I noticed it's actually based on the 2010 census, so between 2010 and 2020, because I counted these here, which are California, and these here, which are, oops, that's not New York. I just noticed that. That's actually Texas. The third one would be New York. And I noticed that in 2010, yes, there were 53 for California and 36 for Texas. So that's what it's based on. So here in Fairness of Apportionment Methods, they talk about these different methods, and there would be Hamilton and Adams and Webster and Jefferson and, well, it should be Huntington Hill as well. And they come across of that, well, they're all somewhat flawed, and we're trying to find the fairest of them that, gives us the most fair outcome. By the way, in this chart here, I meant to mention here, at the very top right, you see the ones that only have like one representative for their particular state, and there should be, I believe, 3, maybe even more: Alaska, Vermont, and Wyoming. And then I'm not sure about the other small states like Rhode Island and Hawaii. They might have more than one. All right, let's see. The next page I want to go to is actually the problem. Where did it go? Getting there, I guess. And so that's actually the problem. Use the Huntington Hill method to apportion the seats in the U.S. House of Representatives based on any one census ranging from 1940 to 2020, and I will supply the data for that. Just from a different math book called Excursions in Modern Mathematics by Peter Tenenbaum. So he has a 2-page coverage here of a brief history of apportionment of the United States. I'm not going to read everything, just a little bit here. As mandated by the United States Constitution, apportionments of the House are to take place every 10 years, following each census of the population. Each state shall have at least one representative, and so on. Following the 1790 census, and after considerable and heated debate, that's why I'm reading this here, because there's more to apportionment here, especially for the House of Representatives, like Senator Hamilton established, and so on, and then vetoed by President George Washington, and Jefferson convinced Washington, and so on. Then Jefferson's method remained in use for 5 decades, up into including, and so on and so on and so on. I'm going to go down here. So then there was John Quincy Adams that would apportion the House using the method we call now Adams method, and a second one sponsored by Daniel Webster, I believe was a senator, that would do the same using the method we call now Webster's method. So we already came across all 4 methods that were being used before the present one. and then again Webster's method, and so on. As a result of a power grab among states, an apportion bill was passed, and so on. And then Hayes versus Tilden, and so on. I'm going to page. Now I might run into a problem here on my desk. So 1882, the Alabama paradox first surfaced. Looking at possible apportionments for different house sizes, it was discovered that for a house of 299 seats, Alabama would get 8 seats. Okay. But if the house size was increased to 300, all right, seats, Alabama's apportionment would decrease to 7 seats. So according to the method they used back then, it produces paradox. Add one more seat and one of the states actually would lose a seat, which means 2 other states would actually win one, right? The one, of course, the one more, and then the other one to make up for Alabama. So it's like, wow. And then it says in 1901, the Alabama paradox finally caught up with Congress. So they left it at that and chose a different number here, 325. The Census Bureau presented to Congress tables showing the possible apportionments under Hamilton's method for all house sizes between these numbers here. Then Maine and Colorado actually were impacted by the same paradox. So Maine would get 4 seats, except for some sizes where they only get 3. And something similar happened to Colorado. And then they took the sweet spot here, 357, which impacted both of them. That's what they're saying here. Exact sweet spot if you wanted to rob both Maine and Colorado of a seat. That was not a coincidence, and faster than you can see, we're being robbed. The debate in Congress escalated into a frenzy of name callings and accusations, with the end result being and so on. And it took another one, 386 actually, which took one away from Maine. Oh, wow. Okay, Webster's method remained in use for the apportionments and so on and so on. And then in 1941, Congress passed a law that established a fixed size for the House of Representatives, permanent method known as the method of equal proportions, or the Huntington-Hill method. 1941 law represented a realization of Congress that politics should be taken out of the apportionment debate, and the apportionment of the House of Representatives should be purely a mathematical issue. Are apportionment controversies then over? Not a chance. So with fixed size house and so on, then 1990 apportionment, Montana was facing, and so on. And the book is probably published back in 2008 or so, so it doesn't mention the latest census in 2010, 2020, especially one in 2020, that produced a very narrow margin between New York and Minnesota, where it's like, wow, if one of them had more people, then it would actually gain 1 seat, or the other one would lose 1 seat. So yeah, a lot of politics involved that I try to keep out of the purely mathematical issue of using the Huntington-Hill method for apportionment to the U.S. House of Representatives. These are the mandates for the apportionment of seats in the U.S. House of Representatives. So the apportionment is based on the census per the Constitution, also that the census occurs every 10 years. There has to be at least 1 representative per each state, also per the Constitution. There are exactly 435 seats in the House of Representatives, according to the Apportionment Acts of 1911 and 1929. And then since 1941, the method used is the method of equal proportions, or Huntington-Hill. And these are the websites that this can be looked up. Notice that I use government websites, so archives.gov for the census here. Then at least 1 per state, again, the Constitution. Exactly 435 seats, house.gov. And method of equal proportions, I found it at census.gov. And of course, you can check those out at many other online sources. This is a website at libretext.org for a math book that covers apportionment. And this is a description of how the Huntington-Hill method works. What's called the method of equal proportions. So the Huntington-Hill method attempts to minimize the percent differences of how many people each representative will represent. And I will try to show that in my Excel sheet for the couple of examples that I have planned. I'm going to go through these 4 steps here. So I will show the standard divisor, which actually I will call quite often the modified and adjusted divisor. Just before it becomes modified or adjusted, it will be standard. About the standard quota, then the geometric mean, which as you see is the square root of n times n plus 1, n being perhaps the number of seats in the House of Representatives, so it's an integer number, times another integer number, so 1 up, take the square root, I will also show that. And then the initial allocation of the seats, and I will just call these seats. Then there's a 5th step. The 5th step is a correction step, where it says change that divisor, that standard divisor here, change it to recalculate the quota and the allocation, because the Huntington-Hill method actually might give a number that is larger than the 435 or smaller than 435, and it needs to be adjusted. And again, you will see this one here as well, how that is being done. All right, this is what you have to do for this project. And then hand in is choose any one of these here, 1940 through 2020, just one that another student hasn't done yet. Don't choose 1930 or 1920 because the Huntington-Hill method was not applied back then. So let's say, for example, you chose this one here. Pull down on the average people here. This one here is still the standard divisor. This is the number of seats, 435, again, Constitution. This one here, pull these here down. And you can see when you compare the standard quota to the geometric mean, well, depending, you would either use the lower quota or the upper quota. This one is smaller than that. It's the lower quota, so 7 in this case. If this one is larger, it will be the upper quota, so 4 in this case, and in fact there it is, right? And then the process, as you do this one here, so for example, this one is larger than that, it's the 43. This one is larger than that, it's the 5. This one is smaller than that, so it's the 1, and so on. As a side effect, states that actually have a geometric mean of 0 and have a very small population, Alaska in this case, still by the Constitution and by the Huntington-Hill method will get that one guaranteed seat. You pull all these down here. What I just showed for Alaska, by the way, happens for Vermont and Wyoming in this case here as well. Pull these all the way down, and 2 too many, needs to be adjusted. So that's the 5th step for the Huntington-Hill method, to correct that. So that you pull this one down. There we go. These numbers again should be basically the same as these here, but 2 of them are different. Same thing with the seats. 2 of these will be different from these. I mean, any one of these 50 here. Pull this one down. I know there is nothing there, but it actually calculates. It just doesn't show it. So pull this one down. And look for apparently 2 numbers where any one of these here is closest to 1.00. Right now I identify Oklahoma and Oregon. Let's see if that's true. 1.0062. Oop, there's one closer here, Connecticut. highlight, in this case Connecticut, highlight, I guess, both Oklahoma and Oregon, but Oregon is actually a little bit closer, which means Oklahoma will actually be spared. So let's see. Pull this one down. Again, there is nothing there, but it actually does calculate for all 50. In fact, there are two negative ones. One is here for Connecticut, and the other one is here for Oregon, which means actually we don't need Oklahoma. And then adjust the correction term here, and that should be in the hundreds or thousands until you get 435 here, and that of course is how the seats are computed, which then will match all of these here, and you will get rid of the negative ones, and you will get rid of all these numbers here, and then you answer a number of questions in the assignment. And yeah, that's basically what you have to do. In order to prep it for students, I will actually take these out again. Again, you're only going to do one sheet because other students will be working on these here. Let me show you a second example here. It's this one. So, again, you pull this one down. Still 435 is required. Pull these here down. Again, you do one or the other, any one of these 1940 through 2020, and submit it. So I'm just going to show you two other examples here. And again, this number being larger than that gives the upper quota. This number smaller than that will give the lower quota. Smaller than that, lower quota. And we can see that, yep, 7, 1, and 9 for these three here. Pull this down here. And in this case, we actually get, there's one too few. So one of these states actually needs to gain a seat. We'll pull this one down here. Again, all these numbers here, the number of people per representative match all these numbers here, except one of them, because it needs to gain the one seat. Can we pull this one down? I know there's nothing there, but the formula actually is there. So pull this one down. And there we go. And again, this time around, you can see we don't have numbers larger than 1. We have numbers smaller than 1. So we're looking again for the number that's closest to 1.00. And because we only have to gain one seat for one state, we only have to look for one number. There's a candidate here, the 0.9938. Oop, there's a better candidate. Missouri, 0.9968. Maybe that's the one. I don't see any other one here. No, I think it seems that it is indeed Missouri. So let's highlight that. There we go. Pull this number down. Again, there is nothing there. But one negative 1 will show up. Oh, 1 will show up. Oh, it wasn't Missouri, actually. 0.9992 for Minnesota is actually closer. And I can see that now. I overlooked that. So let's switch that. The color coding here. There we go. So Minnesota all actually needs to gain one here. It has just too many people for all its representative. So we give it one more seat. The apportionment gives it one more seat, the Huntington Hill method. And that will kick this number down to a more reasonable value within all the others here. In this case here, because the 434 is smaller than the 435, the correction term actually is negative. It's going to be in the negative few hundreds, negative few thousands. You have to see how to adjust this number here for this one to come out to, well, 435. And then this one here will go away, and Minnesota actually will go up to 8 seats there. Okay, again, I will take all these numbers out so people can start over fresh. I'm going to always leave the top one there because these all have these formulas there. we don't want to throw them away, so we have to make sure it's always in the top one.